In this lecture, I'll talk about multiple linear regression, but also I'll review how to read the OR output. So, how do I run a regression? 3 lines. 1, read in the data. Read.csv Pearson Lee simple. 2, run the model. Pearson mod arrow LM linear model child tilde parent. Predict the child type from the parent type. Data equals Pearson Lee. And then summary Pearson model. Summary of the model, telling me about the model. And the output there on the left is what you will see. It gives you everything to do with that model. The first thing is about the model itself. The second is about the residual. Then we have the coefficient. Then we have the standard error. And then we have the model hypothesis. So the model. So our model is just what the command was, lm child tilde parent, using the data Pearson Lee dataset. The residuals. So this is where we need to keep an eye on this. I'll talk about this at the very end of the lecture, but let's just mention it now. The residuals should be centered around 0. So their mean should be 0, and they are. The median should be close to 0, which it is. The minimum and the maximum should be the same, but different signs, and same with the first quartile and the third quartile. The residuals here look okay, and we can talk more about residuals in the class. Now, from the model, like I spoke about in the last lecture, you get your sum of squares in the x direction, sum of squares in the y direction, and a covariance in the x and y direction. So how does the height vary in the x and y direction? Do they vary together, or is there no variance and it's flat? I mean the mean in the x direction and mean in the y direction. Now, x here is once again parent height, y is child height. So now we have a lot more data. From that, exactly as we showed in the previous lecture, we used the covariance divided by the sum of squares in the x direction to calculate beta 1. So that's our beta 1. Beta 0 comes directly from it. We put beta 1 into here. We find the average of x, which we just calculated, average of y, and that gives us our estimate of our beta 0, 41. Here we are with the OR output, and it's there and there. It's immediately with the coefficients. Now, the next thing is each coefficient has to do its own hypothesis test. Is this coefficient significant? Is the intercept significant? Is the slope of the parent significant? And we use the standard residual of the standard errors. So that's the observed minus predicted squared. And the square of that divided by n minus 2, number of points minus 2. And from that, we can calculate our standard error. The formulas uses the standard residual, 4.81, standard residual error. And so to calculate the standard error for beta 1, we do the sum of squares in the x direction, 1 divided by the square root times the standard error. There's 0.371. Similarly for the beta 0, which is the intercept, it's a bit more involved, sum of squares, 1 divided by n, the number of points, the mean squared divided by the sum of squares in the x direction. That gives us 2.4189. And that all is there already in the OR output. Next, we ask, is it significant? So for every single value, as I said, you need a t-value. So we have a t-value for beta 1. So that's the observed divided by the standard error. The observed divided by the standard error. So that's a t-value of 10 and a t-value of 16. If there is more elements, you'd have more t-values. Every single one of these is itself a test. So here we have our t-value. Now, OR also gives you significance levels. And it has this nice little, very straightforward indicator. 3 stars is very significant, 2 stars is a bit significant, 1 star is significant. Now, as I said before, it doesn't matter if it's significant or very significant. Significance is all you care about. After that, you can't say anything. Or it's a very low p-value, does not matter. If you set your criteria to be 0.05, then it is significant. And we have our residuals. So from that, we can also calculate our R squared, which is our variance. How much of the variance in the parent's height does the variance in the child's height explain? So our tall kids, tall parents. So here we have our variance is 0.26. And you're saying that seems low. 12% of the child's height explained by parent's height. I think that seems like a lot. There are so many myriad of factors to predict someone's height. A parent's height alone is probably not enough. But 12.5% is pretty good. Is it significant? That's what this last line is. That says the model is significant. That's the model hypothesis. The very last line actually is the most important line. That's the line you should go to first. It's an F statistic, which is a bit like our chi-squared statistic. It's just a different kind of distribution. It takes in our degrees of freedom. And if this p-value is less than 0.05, it means the model is significant. If the model is significant, then you look at coefficients. If the model isn't significant, there's no point looking at coefficients. So I'm using APA, so American Psychology Association. I just had to write out. A simple linear regression was calculated to predict child's height based on parent's height. A significant regression equation was found, F174, so that's the bottom line, with an R squared of 0.126. So 12.5% of the variance is explained by the model. Child's predicted height is equal to 41 plus 0.38 times parent's height. Child's height increased, and you could say significantly, for each inch in the parent's height. So that's me breaking down the R output. This is what you would see on the screen, and I've just told you where to look. So let's extend this to multiple linear regression. A multiple linear regression, as I said in the first part of the last lecture, you take in more than one predicting parameter. So what would be a good one to do in our height scenario? Well, why don't you include the sex of the child? Because that's a factor as well. If you're assuming boys and girls are the same height, well, that's not, you shouldn't assume that. So you include the sex as well. So now to predict a child's height is beta naught plus the parent height times the sex of the child. So this is what our output looks like. Very similar. Note now, we have two lines. One line for son, one line for daughter, and they're separated because sons are taller than daughters. So let's read it. So we have our linear model, child tilde parent plus chil. Chil is a, now there's one thing that should be noted. You need to know your data. You need to know what each column is called, because each of these input is from the column name. If the name isn't there, then it's not an input. Yeah. Chil has two options. It has son and daughter. And so it's categorical. So it just splits it by son and daughter. Our coefficients, like before, we have parent, but now we have child, and it goes child son. Why does it go child son? It's saying that when child son is 1, add 5 inches, and that's the son's height. If that's 0, which means daughter, you don't add those 5 inches. So you need to also know that son is 1, and that's what it's telling you, and daughter is 0. So sons are 5 inches taller than daughters. So you find out a bit more information. You find out something that indirectly from the model, you've been able to compare between sons and daughters' heights as a function of their parents' heights. And what about our model? By adding in this one thing of the son and daughter as a variable, a categorical variable, we've increased our R squared to 0.3677. That means 36.7% of the child's height is explained by parent's height and is a daughter or a son. That's a 3-fold increase by including one extra variable, which is massive. Now, I should know, every time you introduce a new variable, you add complexity to your model, so you should always take that into account. So a multiple linear regression was calculated to predict child's height based on parent's height and sex. A significant regression equation was found. That's our last line. With an R squared of 0.3677, which is significant. And here's our little formula, 38.56742 plus 0.387 times height plus 5.056 by sex, where height is measured in inches and sex is coded as 0 for daughter, 1 for son. Child's height increased 0.385 inches for each inch of the height of the son's height, and 5 inches for each daughter, for more sons or more than daughters. Now, lastly, where can you go wrong with a linear regression? By not observing these very important assumptions. One, that there is a linear relationship. There doesn't have to be. There can be very complicated relationships. Happiness is meant to be a U-shaped function with respect to age. You're happiest when you're young and you're happiest when you're old. In between, you're not. And that's a U-shaped function. If you try to do a linear regression with that, it will not work. So that's why it's so important to plot your data at the beginning. Now, statistical independence of the errors. In particular, no correlation between consecutive errors. So everything has to be independent. You shouldn't use time series data for linear regression. People do, but you probably shouldn't. And time series analysis is a whole other type of thing you can learn. Now, the variance, the homeostaticity is constant variance of errors. It means the errors should be equally distributed throughout, and more importantly, the errors should be normally distributed. And that's the residual. So the residuals should be around. So you shouldn't have too much clustering of your data together. You shouldn't have 2 points here and 100 points over here. They should have a relatively smooth clustering. So we've covered now a simple linear regression and now a multiple linear regression. These are very powerful tools which are used all the time. People make mistakes with them, and that happens. But as long as you know something about your data, you plot your data, see what it looks like, it should be okay. We will do in class a bit of OR so you can have a look at your data to see maybe it doesn't fit the regression right. And there might be certain points you need to remove. They are much more complicated questions and beyond the scope at this moment. So